Hello and welcome to the second episode of our seminar Falling in Space. We are going to talk about history, as I promised. But first I would like to make a couple of comments. When you look up at the night sky, and I showed you the animation last previous episode, of how the planets are moving with respect to the background stars. This was a central problem that had to be explained by our ancestors. Now, of course, we know, just to emphasize that we are going around the sun as a planet, the blue dot here, and Mars in this example, and all the other planets are going around the sun as well. And it's when we catch up with Mars, in this case, we are moving faster than Mars does. For every about 16 months or so, we catch up with Mars. Then Mars is in the opposite direction from the sun. We call that opposition. And it is around that time, as you can see, that Mars, from our point of view, makes this looping motion. That is the reason why we see the planets move in the sky the way they do. I just want to emphasize that you have that background when you now hear about how our ancestors over the last 2 or so millennia have been grappling with explaining these motions. The other comment I want to make is that if you talk about naked eye astronomy, and it is only relatively recent that we have used telescopes and all kinds of instruments to look further, but we should look at the naked eye. The stars that you see are a maximum somewhere in the order of 6,000 light years away. There are some very massive stars in adjacent arms of the Milky Way galaxy in which we are, which are at about 6,000 light years away, and they are so massive that we can still see them with the naked eye. But that really is the limit. So if you look up at the sky and you look at the stars, you don't look at the whole universe by any stretch of the imagination. What you do is you observe in a bubble, which I've indicated here, to this in terms of its scale, to this artist impression of the Milky Way. So we are in that disk here somewhere where the sun is, and whatever we see with our naked eye is limited to this bubble. We do see the band of the Milky Way galaxy along the sky, and our ancestors, of course, did that too on a clear night. That's because we are inside that disk, and we see the disk all everywhere around us, especially bright towards the center of the galaxy, as this band in the sky. And this has been surrounded with a lot of mythology and also scientific discussion. But this is not relevant in the context that we're talking about, because the Milky Way in the sky is moving exactly the same as the background stars. There was no conflict or no difference in motion that we needed to worry about. I just want to make that comment to give you the basic view that we know now against that history that we're going to talk about. Okay, first up is Aristotle. So this is in the 3rd, 4th century before the Common Era. There were many Greek scholars around that time in the whole era of the classical Greek philosophies. Aristotle was one of the largest, most important in terms of his influence on later scientific thinking. He was a very wide range in his capacities. He has made foundational contributions to philosophy, to biology, and several other scientific endeavors. But here I want to refer to his cosmic view, his view of the world, what it would like, and on the Heavens that was published around 350 before the Common Era. That's a publication that we have. There are two things. One is that he had a strict separation between the sublunary sphere, as you could call it, the sphere below the moon, which is basically here on Earth, which is corruptible, as it is mentioned in the translations. Corruptible meaning that things are not non-permanent. There is birth, there is decay, there is death. There's constant change. There's nothing permanent in contrast to the heavens, which are incorruptible. There, everything is the way it always has been, and it always will be. There's basically no change. They had to accept motion. I'll come back to that, but the principle of that realm of the heavens was that it was constant, always had been, always will be. In terms of the elements, which is basically the foundation of what we now call chemistry, he suggested that there are four elements here on the corruptible realm, in the corruptible realm: earth, water, fire, and air. Earth and water were the heavy elements. They were seeking to go to the center of the universe. That was their motion, their urge to do. That's why the earth definitely was in the center of the cosmos. Fire and air were the light elements. They were going at a tendency to go up and towards the heavens. In the heavens, you had a fifth element, which he referred to as ether. This has been used for many for more than a millennium, maybe 2 millennia, since Aristotle, in different contexts by physicists. But that's the fifth element, or the quintessence, as it was called, which was filling the heavenly realm. And in terms of motion, because the heavens were permanent, and the only motion that you could accept was constant spherical or circular motion, and that was the explanation for the planets and also the moon and the sun. They were each attached to a particular sphere, which was then rotating in a constant rotation with a constant speed. And that is what we saw. And he had the order right: moon, in terms of distance, moon, Mercury, Venus, and then the sun, because we look at it from the Earth's point of view, which is in the center, and then Mars, Jupiter, and Saturn. Those were the naked high planets. Because of this construction, which was really philosophical, he could not explain these irregular motions of the moon and the planets. That was not really an issue at that time. This is a different way of thinking of the classical Greek. They weren't really bothered with doing observations very much. It was more the abstract thinking that gave you knowledge, that expanded your knowledge. That was kind of the philosophy. But this is really the start of this, what we call the geocentric view. And then we have the next one is Ptolemy, Claudius Ptolemaeus. In English, you say Ptolemy. Okay, this was 400 years later. He had a very famous publication here. He wrote several things, extremely foundational and long-lasting in terms of its influence. But this is the Almagest, which is the Arabic name, the Arabic title. The original title was The Great Treatise. Almagest is the Arabic title, where he collected the ideas of all of the classical Greek philosophers at the time. Aristotle, definitely. This is why I started with Aristotle. Hipparchus was another Greek philosopher who is famous even today for the fact that he that arguably made this first star catalog. Ptolemy expanded on that and included it in his Almagest. This was an extremely influential foundational work for astronomy ever since that time, for at least 1.5, maybe 2 millennia after that. I'll show you this in the course of this history description. It was a very detailed mathematical treatise as well. It was not just making reference to what Aristotle and others had said. It was a very intricate description of the cosmological system, you could say, where definitely the Earth was in the center. And he had intricate geometric ways to explain these irregular motion of the planets that we described. And this is one of the key aspects of this publication, and this refers to what we call the Ptolemaic system. This is what I just mentioned. This was so well written and so impressive that it really was the foundation for astronomy and cosmology, if you want to use that term, for the next 1.5 up to 2 millennia. It's unbelievable, but also understandable. Well, it's maybe a contrast, but I hope you understand what I mean. Here's an example of the geometry that he had in mind. It's based on epicycles, which you may have heard of. But the center is the center of this construction is what's called the deferent, this large circle, which is rotating in a uniform way in one direction. The center is also not in the Earth exactly, so it's often called a geocentric system, but it is actually a quasi-geocentric system. The Earth is not really in the center. He had to move that away to match the peculiar motions of the planets that were observed at the time with the accuracy of that time. And then there is an abstract point, a theoretical point, which is moving uniformly in that large circle, which is the center for a smaller circle, which is the epicycle. And the planet is moving in a constant motion, circular motion, around that abstract point, which itself is moving uniformly along the deferent. So that is basically the way in which he could describe motions of the planet. And it worked really well. You can even do this today. And now with our modern instrumentation, we have far more accuracy in terms of position measurement. This would not be sufficient, but for that time, it was really a very clever way of describing the motion of planets. And the basic concept was that, and this is really important to understand historically, that it was based on uniform circular motion. There couldn't be anything else than that, because this was in the heavens, this is the uncorruptible realm. So that is what we refer to as the Ptolemaic model. And then I need to mention Aristarchus because he was kind of an outlier, but he was way ahead of his time. We have no publications left him directly, but indirectly we have information by other scholars mentioning him. He apparently considered the sun to be a central fire, and he related central fire, meaning that it should be in the center, not the Earth, but the sun should be in the center. But also that other stars are basically the same thing. They are central fires. He even very likely suggested that if planets go around the sun for us, then other stars could have planets going around them. This is, of course, way ahead of his time. And there were others as well, Greek philosophers who had similar ideas. But this was ignored because the influence of the Almagest by Ptolemy was far too strong, and that overruled any other alternative ideas. And then more than a millennium later, just imagine a millennium, 1,000 years, where Ptolemaic astronomy had been the foundation, translated in Arabic and Latin. I should say that about the Almagest, the European, in many generations later, European astronomers were confronted with the Almagest as in the Latin translation, which was translated from Arabic. It was much later that historians and scholars went back to the original Greek version of Ptolemy, etc. Okay, so this is more than a millennium later. We have Copernicus. He is known as the father of the heliocentric model. That is his very fundamental contribution. But there were others as well before him, around him, in the same time. That was the time that they started to wonder about these originally Greek models for the cosmos. There were notable errors in the predictions based on the Ptolemaic model. For instance, eclipses. They're of course very distinct. You can't mistake them, but they were not predicted at the correct time. There were also disturbing inaccuracies in the calendar. It's a different topic that doesn't really relate directly to the motion of planets that we talk about here. But I just wanted to mention that. I encourage you to study the history of calendars. It's an extremely interesting topic. Julian Caesar, in his time, that was about the 1st century of the Common Era. He was, at that time, the seasons were really wrong with respect to the calendar. It was actually very dramatic. So he corrected this calendar, that is the Julian calendar, and later Pope Gregorius, much later, realized that the seasons were again slipping away from the observations from the calendar predictions, and he made another correction. The length of the year, which is the time that the sun takes to go around the sun, is 365 and a quarter day, roughly. It is what Julius Caesar's advisors, noted. We should, every 4th year, we should make an extra day, put an extra day in our calendar. That's the Julian calendar. That's why we have leap years. Gregorius and his advisors noted that was not good enough. The calendar was still deviating. Why? Because the actual time it takes, of the length of a year, is 365.248 or something, a little bit less than 25, a quarter days. And Gregorius made the correction that at the whole century, which is also divisible by 4, but then you skip a leap year. That's the Julian Gregorian calendar that we are still using today, which will last for another 10,000, maybe 20,000 years or so. But we don't need to worry about that again. I'm just making this sidestep because it's a really interesting. But anyway, at that time, around this era of Copernicus, they noted not only these inaccuracies in predictions about planetary motion, but also the problem with the calendar. And this raised the alarm, in a sense, that we needed to do better than that. This was really the motivation behind this. He was not an astronomer himself. He had studied at university. He was an intelligent person, definitely. But he worked as a physician, as a lawyer, and as an administrative work for the church. But he had studied astronomy sufficiently that he could find a description, which has been a major publication, of a worldview, a cosmology, where the sun was in the center, and then explaining the motion of the planets as we see them much better than in the Ptolemy model. It was a more elegant description because you didn't need these very involved geometric constructions that Ptolemy had given. Although, and this is something that we really need to realize, that the actual accuracy of predictions of planetary events based on this model was not necessarily any better than it had been before, in the Ptolemaic model. He published this in the year of his death in 1543. Let me first describe the model in a little bit detail, though. Then I go to two misconceptions that we need to correct, because I have been brought up with those misconceptions myself. So the model is that the sun really is in the center of the cosmos. You have the order of the planets correct. Here's the Earth. We have Mercury, Venus, and then the Earth with the moon going around it, etc. Sun is in the center. He still had to use the epicycle construction, although the prediction of the explanation of the motion planet was much more elegant in this way than Ptolemy, but he still had to use this epicycle construction to really match the observational accuracy of the time. That means that the predictions based on this model, it was far more elegant, but based on this model was really not much better in quality. This is something we need to realize. Because this was a very rigorous publication based on mathematical constructions, it was really admired by his contemporaries and also the next generation. But it is wrong to suggest that this heliocentric view was immediately accepted. It took more than a generation later before this became more common in terms of its acceptance, that the sun was in the center rather than the Earth. The other misconception is that he published this only in the year of his death because he was afraid of the Catholic Church, the repercussions of the Inquisition in the Vatican, who wouldn't like this idea because it was against the dogma of the Church. This is not correct. This problem came later, and I will come back to that. He did not have real issues with the Catholic Church. He was he had good contact with the then Pope Paul III. There was no conflict. The reason that he published this when he realized that he was dying, or going to die, was that he was a perfectionist. He didn't want to give up improving on this publication. So this, on the revolutions of celestial orbits, really a foundational publication, which really puts the sun in the center. But this was not immediately accepted. It took more than a generation before this took hold among the astronomers. So this is about Copernicus. And now we go to the next person, Galileo. He is arguably one of the greatest physicians ever. He made many contributions that are foundational for motion, studying motion, like Newton. I'll talk about Newton later. Who formulated these laws of motion. The first law of Newton, as we call it now, was actually stated by Galileo. Also started basically thinking about relativity. I'll talk in another seminar about special relativity. When we started that, I'll show you that there was something that we now call the Galilean principle, which is the start of thinking about relativity, which Einstein picked up. And Galileo never used the word relativity, but he definitely thought about it. One, in the context that we're talking about here, a very important contribution by Galileo is based on the fact that he made a telescope. It was invented in Northern Europe. This principle of having two types of lenses on either end of a tube. He heard about it and he fashioned his own version of a better quality than anyone else had done at the time. So it was a marvelous instrument which you have a magnification of something like 30 times or so. And he was the first to put that instrument and aim it at the heavens and look at the bright objects in the sky. And he observed the moon, and he saw craters and mountain ridges on the moon that nobody had seen in anything of that detail before. Famously, he observed the phases of Venus. He saw that the Venus was not a circular object in the sky, but it had changing phases, just like our moon has. Probably most dramatic, he observed Jupiter, and he saw 4 star-like dots close to Jupiter. And if you look from night to night, he saw that they changed their position. So he concluded that these are moons that need to go around Jupiter. You can do this yourself, by the way, if you have binoculars. Look at Jupiter and repeat that from night to night, and you will see those 4 dots. Sometimes you don't see all 4 because 1 or 2 of them could be behind or in front of Jupiter, but they will reappear, and you will be able to reconstruct that these are 4 moons that go around Jupiter, which was completely against the idea that everything, that's the Ptolemaic idea, that everything would go around the Earth. So there were things that went around other planets. Probably another thing that he observed at great peril, because it was extremely dangerous, he looked at the sun with the telescope and he noted sunspots. He made drawings and sketches of what he observed. And this led to his first publication in this context, which is extremely important, in 1610, The Starry Messenger, wonderful title, where he described what he had seen. And this really woke up the Catholic Church, the Vatican. So this was a generation later than Copernicus. Here the Catholic Church felt, hey, this is too much in conflict with our dogma. The attitude in the Vatican had also changed. There was a different pope. They were far more conservative than in the previous one. So this really got the attention of the Catholic Church, his first publication, which was widely copied and read with great interest. And then his second publication in this context, which is really important historically, is that of the Assayer, it's the English translation in 1623, where he realized and explained that science should be based on evidence, based on observations. This was totally new for that time. Now we know, and everybody who has basic understanding of modern science knows that any theory you pose needs to be contestable and needs to be evidence-based. This is how we do science. But this was really the start of that philosophy. The Greek philosophers had a completely different view. They were establishing the acquire of knowledge as based on authoritative reasoning. You had the authority, you were a scholar, and then you really thought hard enough that you could gain knowledge. But here is the new way, the new direction to do science, which is historically very important. Now remember 1610, in 1616, the Roman Catholic Church put the Copernicus publication, which he published at his deathbed in 1543, on the index of forbidden books. So that's when they went back to Copernicus, the Catholic Church went back to Copernicus and said, hey, this is not going in the right direction. This Copernicus book is on the index. That's a forbidden book. They couldn't do anything against Copernicus, but he was dead for 73 years or so. So it was the next generation. But this was more or less triggered by Galileo, by his publication in 1610, the Starry Messenger. And then came his big publication in this context, which is called the Dialogue Concerning the Two Chief World Systems. He knew that he had a risk of the anger of the Catholic Church. He kind of diplomatically, although I don't think he was much of a diplomat, he was too rigorous in his thinking, but he described this idea of the Copernican system in the context of a discussion between two people. One was in favor of the Ptolemaic model, the other in favor of the Copernican model. And then he was, which clearly the third person was himself. He was kind of in between that, and he just followed that discussion. But it was clear enough that he was really promoting the Copernican idea, that this really brought him into conflict with Rome, unlike Copernicus. And I have links in the course booklet if you're interested. It's a very intricate situation around his prosecution and trial, ultimately in 1633. It's full of intrigue. There are still investigations going on by historians to get to more detail, but there were intrigues both in the Vatican between cardinals. There were the controversies for Galileo himself among his colleagues, other scientists, some of whom saw an opportunity to work against him. There's a lot of intrigue. It's a really drawn out story, actually. What was in Galileo's benefit was his age at that time, but also that he was able to defend his views really rigorously. They could not find an actual statement that would put him in the category of the heretics. They had a convincing method to find the truth of people, which we now call torture. He escaped that because of his age, and also the little bit of respect that he still had amongst the cardinals in the Inquisition. So the ultimate end was that he got house arrest from the age of 69. He could not publish anything anymore, and he couldn't communicate with other scientists. He used the remaining time of his life, which was another 9 years, to summarize all his studies, etc. So that's the story of Galileo, and also in the context of this discussion we have in our seminar, the explanation of the motion of planets. This was really a strong support of the Copernican system, of the heliocentric system. In the next episode, I'm going to talk about someone who is referred to as the last naked eye astronomer, who has made very major contributions to a new way of thinking about planetary motion.